Hi guys, let's learn about an electrical circuit subject. This video is going to be about passive high-pass filters. A quick reminder, you should learn about low-pass filters before going on with high-pass filters. High-pass filters show the high-pass frequencies pass through unchanged and the low frequencies get attenuated. The reason why this works is that the voltage across the capacitor cannot instantaneously change. So if there's sudden fast change on the input voltage, it will instantaneously appear on the output side of the capacitor. So really high frequencies pass straight through the capacitor as if it was just a piece of wire. Also, series capacitor block DC. After all, they are just parallel plates that never actually touch each other. And in DC steady state, they are basically an open circuit, so you get 0 volts on the output. And in between these two extremes, we get a frequency response curve like this. It is very similar to a Bode plot of a low-pass filters, it's just flip around. At high frequencies, the signals passes straight through the filter unchanged. As the signal approaches cutoff frequency, it starts to decrease in amplitude. At the exact cutoff frequency, the signal's amplitude is reduced by 3 decibels or 29%. Soon after that, the amplitude does off at 20 dB per decade, which means that for every time the input frequencies get reduced by a factor of 10. And the other cool similarity is that the equation for calculating the cutoff frequency is exactly the same as for low-pass filters. Now, let's look at some examples. I'm going to design a high-pass filter with cutoff frequency of 30 kHz. I'm going to choose 10 kilo ohm resistor, so I only put a light load of the function generator. Next, I use the rearranged cutoff equation that lets me calculate the value of capacitor I need. It turns out that I need a 537 picofarad capacitor. That is a weird non-standard value, so I'm going to combine some capacitor to get closer to the value I want. This inaccuracy will affect the cutoff. So, with the 60 Hz on the input, the high-pass filter is barely letting anything pass. At 10 kHz, about half the signal is being let through. At 30 kHz, the output is roughly 29% less than the input. Finally, a 3V sinusoid laid on 9V DC on the input. The high-pass filter completely removes DC offset and you're left with a 3V sinusoid. Another interesting thing to see is how high-pass filters affect square waves. With the 600 Hz square wave, you can see that the only sudden fast edge transition are passing through, but the part of the square wave that's just a flat line sets blocked out. If we crank the frequency up to 6 kHz, a little more of the original wave shapes gets through. At twice the cutoff frequency, we get a waveform like this. And at 1 MHz, almost everything gets through. Another example is, over here we have a 9V and a 5 kilo ohm resistor which are used to power the microphone. This gives us a 20 mV peak-to-peak signal load on top of the 9V DC bias. Over here we have the amplifier configured for a gain of roughly 100. The idea is that I want to take the 20 mV from the microphone and amplify it to 2V so I can hear it on a pair of headphones. Now in between the microphone and the amplifier I have a high-pass filter. But what would happen if I didn't have that filter? If I didn't have the high-pass filter here, the amplifier would get 9V DC on the input and it would try to multiply by 100. I obviously can get 900V out of the 9V supply and the amplifier's output would just end up maxed out to the plus 9V rail. With a constant 9V DC output, there's not going to be any audio and you seriously risk damaging your headphones. The high-pass filters remove the DC components of the signal coming out of the microphone so that the amplifier only amplifies the tiny 20 mV AC signal. Using the cutoff frequency equation, you can see that the cutoff frequency is 15.9 Hz, so any frequency above that get passed through into the amplifier stage. The result is a 2V AC signal on the output of the amplifier suitable for driving headphones. Finally, do you see how I use a 100 kilo ohm resistor in a high-pass filters? Well, there's a reason for that. Having a high resistance value there will ensure that I don't overload the microphone unamplified output. So that's it for me. Thank you for watching.
Created using Powtoon.